So imagine you're sitting down to solve this massive, like 10,000-piece jigsaw puzzle. You've got the corners laid out, you're starting to build the edges.
Right, making some good progress.
Exactly.
Hmm.
But every time you blink, someone reaches over and just throws a handful of your pieces into the trash.
Oh, wow.
Yeah, and you have absolutely no idea which ones they took until you desperately need that one specific piece to finish the sky, and it's just gone.
That sounds completely maddening.
It is,
Yeah.
but, I mean, that maddening scenario is exactly what is happening inside the brain of modern artificial intelligence right now when we ask it to do long, complex reasoning.
It really is. I mean, the AI industry is hitting a very real physical wall here. We're asking these models to read entire books, write complex software from scratch, or, solve multi-step mathematical proofs.
Which takes a lot of processing.
Right. Doing that requires holding onto a massive chain of thought. But the smarter these generative AI models get, and the longer they think, the more memory they just completely devour.
And that's exactly why our mission on this deep dive today is to explore a potential way out of this trap.
Yes, a very exciting way out.
Because if you're sitting at home right now, trying to run a local AI model on your own gaming PC, or maybe you're a developer hitting constant out-of-memory errors on a cloud server, you have definitely felt the pain of this.
Oh, absolutely. Everyone in the space is feeling it.
So we're unpacking a newly released paper from a powerhouse team of researchers at MIT, NVIDIA, and ZJU. It's called TriAttention. And it is, well, it's a fascinating shortcut.
It's brilliant, honestly.
Yeah, they're using, like, high school level trigonometry to effectively compress an AI's memory. And they're seeing models run 2.5 times faster, using nearly 11 times less memory without losing their intelligence.
And we're going to look under the hood of how this actually works, because this isn't just, a software patch. The researchers found a way to map out the hidden internal structures of how a neural network prioritizes information.
Right. But to really grasp the elegance of their solution, I think we first need to look at the mechanics of why an AI runs out of memory in the first place.
Yeah, that context is crucial.
So when you are chatting with a large language model, say like DeepSeek R1 or Quin's Warn, it's generating its response just one single token or word fragment at a time.
Right. And every time it spits out a new word, it has to ensure that word makes logical sense in the context of everything it has already said.
Plus the massive prompt you gave it at the start.
Exactly. And to do that without constantly rereading the entire conversation from scratch, it keeps a flawless running transcript stored in what is called the key value cache, or, KV cache.
The KV cache.
Yeah. For every single token, the model stores a key vector and a value vector.
So, if I ask an AI to write a sprawling 30,000-word piece of software, it has to hold the keys and values for all 30,000 tokens in active memory.
Yes, and that takes up a colossal amount of physical RAM on a graphics card. I mean, it scales linearly, and very quickly it just eats up all the available hardware space.
It's just a massive bottleneck.
Right. So the industry's initial attempt to fix this was simple compression. Existing methods, like SnapKV or RKV, try to save space by pruning the cache.
Kind of like throwing away puzzle pieces.
Exactly. They basically look at the AI's internal attention scores, decide which tokens the AI hasn't paid attention to recently, and just delete them.
I mean, on paper, that sounds pretty reasonable. Like, if the AI hasn't thought about a particular line of code for 10 minutes, maybe it's safe to throw it away to make room for new thoughts.
Well, the fundamental flaw lies in when those compression methods are looking at the data to decide what's important.
Okay. When are they looking?
They're looking at the vectors after positional rotations have been applied. It's a state known as the post-rope E space.
Okay, let's unpack rope E for a second, because this is kind of the crux of the whole problem, right? Rope E stands for rotary position embedding.
Right.
And, like, how does an AI which only understands math know the difference between the sentence, "the dog bit the man," and "the man bit the dog"? I mean, the words are identical.
Right. The meaning is entirely dictated by the order of the words. So modern AI uses rope E to solve this by treating a word's mathematical vector like the hand on a clock face.
Like a clock hand. Okay.
Yeah. If the word dog is the second word in a sentence, the AI takes its representation and literally rotates it 2 ticks around a high-dimensional circle.
Ah, I see.
If dog is the 20th word, it rotates it 20 ticks. So the angle of rotation fundamentally encodes the word's position in time and space.
Okay, wait. So every time the AI generates a new word, the query vectors it uses to search its own memory are, like, constantly rotating forward.
Exactly, which means the angle is always changing. If you try to observe the AI's attention in this post-row B space, you are looking at a moving target.
Oh, wow.
Yeah, because the queries rotate with every new position, their current angle only aligns well with the most recent tokens. You only get a clear picture of what the AI cares about for a tiny window of maybe 25 tokens.
And anything older than that.
It has rotated so far out of alignment that its current attention score looks artificially low.
So current methods are like trying to figure out which pieces of that massive jigsaw puzzle are important, but you're only allowed to look through a rapidly spinning keyhole.
That is a perfect analogy, actually.
Because by the time a puzzle piece becomes relevant again, it might have already been thrown in the trash.
Right, and that aggressive deletion completely breaks the AI's internal logic. Like, let's say a critical math variable is defined on page 1 of a massive prompt.
Okay.
The AI might not need to plug that variable into an equation until page 50, but during that long, dormant period, the traditional compression methods see that the variable is getting zero attention through their tiny rotating window.
So they delete it to save RAM.
Exactly. And when the AI finally reaches the final equation, it reaches for that variable, finds empty space, and the reasoning just collapses. It hallucinates an answer or just outright crashes.
Wow. Okay, so judging importance through the spinning keyhole of post-rope attention is just inherently broken.
Totally broken.
So the MIT and NVIDIA team, they recognized this chaos and decided to just step outside of it, right? They completely ignored the vectors after they had been rotated and instead looked at the raw data before the rotation occurs, the pre-ropey space.
Right, because before that positional rotation is applied, the vectors are completely unaffected by where they sit in the sequence.
Okay.
And when the researchers mapped out these pre-row P4E and key vectors across various models, they found a structural phenomenon they named QK concentration.
Which means these raw vectors aren't just like a random cloud of numbers floating around in the void.
Far from it. Across over 90% of the attention heads in models like Qwen 3, the query and key vectors cluster incredibly tightly around fixed, non-zero centers.
Really? They don't scatter at all based on context?
Nope. The researchers measured this concentration using a directional statistic called mean resultant length, or R. An R value of 1.0 indicates perfect, absolute concentration at a single point.
And what kind of numbers were they actually seeing?
The vast majority of these attention heads were consistently hitting R values approaching 1.0.
Oh, wow.
Yeah, and this remained true regardless of the input data. You could feed the model a complex calculus textbook, a block of raw Python code, or just a casual chat transcript about baking bread.
And those central points just did not move.
They did not move at all.
Okay, so to bring this back to a physical space, if the post-row B data is this chaotic, spinning night sky where it's impossible to track the constellations, looking at the pre-row B data is kind of like finding the North Star.
Yes.
It is a stable, fixed anchor point that just doesn't move no matter how much the Earth spins beneath it.
That's exactly it.
Yeah.
And those fixed anchors provide a completely reliable map. Because they're highly concentrated and intrinsic to the architecture of the model itself, they give us a blueprint of how the AI prioritizes information.
Entirely independent of that chaotic positional spinning. Okay, but having a North Star is great for navigation. But how do we actually use these static anchor points to compress memory? Like, how do we go from stable pre-row E vectors to actually saving massive amounts of RAM on a graphics card without deleting the important stuff?
Well, this is where we plug those stable anchors back into the math, specifically using trigonometry.
Okay.
The rotary position embedding, we talked about the clock face rotation, is mathematically built on sines and cosines. That's how you calculate angles in a circle.
Right, the classic SOH CAH2A from high school math class. We've all been there.
Exactly. So the researchers realized that if the pre-row B centers are practically static constants, you can just plug those constant values directly into the row B positional formula.
Wait, really?
Yeah. And when you feed static numbers into a formula built entirely out of sines and cosines, the wildly complex, unpredictable attention calculation collapses into a clean, predictable trigonometric wave.
Wait. It creates an actual wave, like a
Yeah.
literal peak and valley graph.
A literal wave mapping attention versus distance. Because the input values are constant, the resulting sine wave perfectly predicts an attention head's distance preference.
So the wave dictates what it wants to look at.
Right. The wave dictates that certain attention heads will always peak when looking at nearby tokens. For other heads, the wave stretches out, peaking when looking at distant tokens.
That's wild.
The AI's preference for how far back in time it wants to look is entirely encoded in those stable centers, and it can be flawlessly modeled by this trigonometric function.
That is just mind-blowing. They took the black box of AI attention, this mysterious process we usually can't predict at all, and turned it into a simple, predictable high school math function.
They really did. And based on this, they built their new scoring system called TriAttention. The foundation of TriAttention is a metric they call S-trig.
S-trig.
S-trig uses this mathematical wave to score every single token purely based on its distance. If a token happens to sit exactly at the peak of the wave for a specific attention head, it gets a massive score and is locked into memory.
So S-trig is essentially mapping out the ideal architectural distances the AI naturally wants to access.
Yes, exactly.
But here's where it gets really interesting, because the researchers realized their beautiful wave had a blind spot, didn't they?
A very significant one, yes. S-trig assumes the vectors never deviate from their center point, which isn't perfectly true. But more importantly, scoring, purely based on distance, creates a vulnerability regarding the actual content of the word.
I see. Like, what if a word is perfectly positioned right at the absolute peak of the wave, meaning it's the exact perfect distance away, but the word itself is just the or, and?
Exactly.
That's a completely meaningless low-impact token. If we only use the wave, we are saving garbage data just because it happened to be standing in the right spot.
Right, and that scenario would bloat the cache with useless data all over again. So to counter this, TriAttention uses a second component called the S-norm score.
Okay, S-norm.
Norm refers to the magnitude, or the sheer mathematical weight and impact of the vector itself. So S-norm completely ignores the distance and just asks, is this token actually carrying heavy semantic meaning?
So you have S-trig looking at the perfect distance and S-norm looking at the actual weight of the word. How does the system decide which score to listen to?
It balances them dynamically using that R value we discussed earlier, the measure of how concentrated the vectors are.
Oh, that makes sense.
Yeah. If a specific attention head has an extremely high R value, meaning the vectors are incredibly stable and tightly clustered, the system heavily trusts the trigonometric wave. It leans on S-trig.
Because the North Star is shining brightly, so we completely trust the navigator.
You got it. But for the minority of attention heads where the R value is lower, where the vectors are a bit more scattered and deviate from the center, the system automatically shifts its strategy.
It stops trusting the wave.
Right. It reduces its trust in the wave and leans heavily on the S-norm score. It falls back on the actual magnitude of the tokens to weed out the weak, irrelevant data. It is an incredibly elegant, self-correcting mathematical system.
Okay, but mathematical elegance in a vacuum is easy, right? It's easy to make a clean sine wave on a chalkboard.
Sure.
What happens when you force this elegant wave to actually do the brutal, messy work of multi-step calculus or complex reasoning on a constrained computer? Like, does this shortcut actually survive contact with reality?
Oh, the benchmarks from the paper show that it doesn't just survive, it absolutely dominates the older methods.
Really? Let's hear the numbers.
Let's look at their performance on the AME25 math benchmark. This is a grueling series of competition-level mathematics problems that require intense, deeply nested reasoning.
The hard stuff.
Yeah. They ran this using the Quen 38B model, allowing it to generate up to 32,000 tokens of thought to solve the problems.
That is a massive context window for a reasoning model. So what's our baseline here? Like, if we give the AI infinite memory and don't compress anything at all, how well does it score?
The uncompressed baseline, called full attention, achieved an accuracy of 40.8%. That is the gold standard for this specific model on this test.
Okay, 40.8%. And what happened when they forced the AI to use the older compression methods, the ones looking through the spinning keyhole?
Using RKV, the leading baseline competitor, under a heavily constrained memory budget, the AI's accuracy plummeted to just 17.5%.
Wow, it lost more than half of its intelligence.
Because it was actively deleting those dormant puzzle pieces, it would define a mathematical rule early on. The RKV system would delete it because it wasn't using the next 20 tokens, and then the model would just fail the final proof.
That's brutal. And under those exact same tight memory constraints, how did TriAttention perform?
TriAttention matched the full attention accuracy exactly, 40.8%.
Wait, really? It matched exactly. No intelligence lost at all?
None at all. Furthermore, while maintaining that perfect reasoning accuracy, the system achieved a 2.5 times higher throughput.
Wow.
It was generating tokens 2.5 times faster than the baseline, while utilizing a massive 10.7 times reduction in KV memory.
Okay, wait. Let's really isolate this to make sure we understand the mechanism. Because the math test is impressive. But how do we know for an absolute fact that TriAttention isn't just getting lucky?
What do you mean?
Like, how do we know it is specifically protecting those intermediate, dormant puzzle pieces we talked about?
Ah, well, the researchers actually anticipated that skepticism, so they designed a stress test called the Recursive State Query Benchmark. It's fundamentally a depth-first search simulation.
A depth-first search. So imagine a massive digital filing cabinet. The AI opens a folder, finds another folder inside, opens that, finds another, and just keeps going down this deep, nested rabbit hole of information.
Right, and eventually it has to accurately backtrack its way all the way out to the top level.
To backtrack successfully, the AI must remember the exact path it took. It needs a breadcrumb trail.
Exactly. And if you increase the depth of that search, you create immense pressure on the AI's intermediate memory.
I bet.
At a recursion depth of 16, the competitor method, RKV, suffered catastrophic memory loss. Its accuracy fell off a cliff, dropping from 61% down to just 31%.
Oh, man. So the AI was completely trapped in the rabbit hole because its memory compression had deleted the breadcrumbs.
It was completely lost.
And TriAttention.
TriAttention held strong and maintained high accuracy all the way down and back up. The trigonometric wave actively identified and protected the breadcrumbs, proving definitively that it preserves intermediate reasoning states.
This all builds to, honestly, the most practical, exciting part of the paper. Everything we've talked about translates directly into what you can do on your own hardware at home.
Oh yes, this is the real-world application. They tested this using an AI agent called OpenClaw. OpenClaw is a multi-turn agent designed for practical tasks. They tasked it with reading 6 different markdown files, analyzing all the disparate information, and synthesizing a comprehensive weekly report.
That is a very heavy, context-rich workflow. And they tried to run this entire operation on a single NVIDIA RTX 4090 GPU, right? Which has 24 gigabytes of memory.
Correct.
That sounds like a decent amount of RAM for a gaming rig, but for an AI.
For a massive model like Qwen 332B, it is microscopic. The raw weights of the model alone consume almost all of that 24 gigabytes before you even start thinking.
Which leaves almost zero budget for the KV cap.
Exactly. So when they tried to run the OpenClaw agent to read those 6 documents using standard full attention,
I guess it crashed immediately.
it hit an out-of-memory error almost the second the context started building. The process just completely died.
But when they activated TriAttention,
The agent ran flawlessly from start to finish.
that's incredible.
The trigonometric compression packed the cache so efficiently that it stayed well within the tiny remaining memory budget. The AI ingested all 6 files, ran its analysis, and wrote the full weekly report entirely locally on a single consumer graphics card.
Which proves that the massive memory requirements of modern AI aren't some unchangeable law of physics. Our context windows are just currently filled with redundancy.
Yes, exactly.
We don't necessarily need endless racks of incredibly expensive server memory to achieve deep reasoning. We just need a smarter, mathematically sound way to filter what the AI holds on to.
This research validates that intelligent pruning can completely replace raw hardware brute force. It's a huge step forward.
So to pull all of these threads together, we started by looking at the immense bottleneck of the KV cache. We saw how current methods fail because they look at the chaotic, spinning post-ropey attention, accidentally throwing away crucial facts and breaking the AI's chain of thought.
And then we followed the researchers as they stepped back into the pre-ropey space, discovering those stable, highly concentrated anchor points across the attention heads.
Right, and the stroke of genius was plugging those stable anchors back into the math. They used high school sines and cosines to generate a clean, predictable trigonometric wave, balanced it with the raw magnitude of the vectors, and created a self-correcting system that compresses memory by a factor of 10.
Truly remarkable.
It matches uncompressed intelligence, it runs faster, and it actually fits on consumer hardware.
You know, the elegance of it leaves me with a broader structural question about the future of this technology.
What's that?
If modern AI models naturally organically organize their internal attention into predictable, wave-like trigonometric frequencies, almost like physical harmonics or musical chords, what does that tell us about how neural networks actually learn?
That's a great question.
Because we discovered these hovering centers and trig waves by accident, observing the models after they were already trained, could the foundational AI architectures of tomorrow be explicitly designed around these trigonometric harmonics from day one?
Wow. That is a staggering concept. building an artificial brain fundamentally tuned to the natural frequencies of attention, rather than just throwing a mountain of computing power at it and hoping it figures out how to think.
It could change everything.
Well, thank you for joining us on this exploration into the architecture of AI memory. It turns out, fixing the limits of a supercomputer isn't always about installing more RAM. Sometimes it's about stepping back, looking past the chaos, and finding the hidden wave in the machine. Keep questioning the boundaries of what's possible, and we will catch you on the next deep dive.